All right, welcome everyone. I am JJ. Let's tackle an example problem. So we're going to say, let's find IX and IY for our composite area that we have here. So let's come in and just recap a little bit. We're going to need to use the parallel axis theorem for this. The parallel axis theorem tells us our moment of inertia about any axis I want to take a look at. That could be my x-axis, my y-axis, any point in there. Is going to be equal to the moment of inertia about the centroid of my object, the centroid of the individual piece, plus my distance in between these two sets of axes, they have to be parallel for this, squared times the area. So if I'm looking for Ix or Iy, I need to break this up into objects. We can work with rectangles and semicircles, so let's start there. I'm going to call shape 1 is my rectangle, then I have a negative semicircle. We'll call it shape 2. So if I'm looking for my Ix, or my I in general, I could say my I should be my I for the rectangle, I1, minus my moment of inertia for the semicircle, minus I2. So let's come in and find those. For Ix, this would get me in one big equation. I need to move that down just a little bit. My Ix should be my Ix for the rectangle minus my Ix for the semicircle. So Ix should be, we'll get the rectangle first. We would have base times height cubed, or my moment of inertia about the x-axis is my moment of inertia about the centroid of the rectangle, which should be I bar is the same thing as Ix prime, base times height cubed over 12. So my base is 100 times my height isn't 30. 30 is the radius. The diameter is twice that. So times 60. Times 60 cubed divided by 12. Plus d squared a. What's my distance from the y-axis, from the x-axis to the centroid? I'm doing Ix. So from the x-axis to the centroid of each shape. Well, the centroid of shape 1 is just in the dead center of it. The centroid for shape 2 is in the y direction, up in the very center of it. In the x, though, it's 4r over 3 pi into it. So we can come and work with this. Also, my equations, I have to be able to reorient this. This is set up so my x goes perpendicular, my y goes vertical. My shape is rotated, though, so I kind of just have to trade my x and my y equations in here, and my formulas for everything. So my plus d squared, though, would get me plus my distance from the x-axis to the centroid of my shape. Well, that's just the radius end. Plus 30 squared times the area. My area of a rectangle is base times height, so times 100 times 60. That'd be half of the parallel axis theorem for Ix. I can add into that plus my moment of inertia for the rectangle, which we know we're actually subtracting because it's negative. So minus my moment of inertia for a semicircle. We're looking at, for x, I go perpendicular to the flat side of the semicircle. And here, perpendicular to the flat side is the y dimension here. So I'm going to grab Iy, pi r to the 4th over 8. So minus pi times my radius is 30, 30 to the 4th over 8. Plus d squared a. So plus, what's my distance in the y direction from the x-axis to the centroid? That's just the radius. 30 squared times the area, pi r squared times 30 squared. Or this is going to get us in here. Ix is 7.2 times 10 to the 6th millimeters to the 4th minus 1.59 times 10 to the 6th millimeters to the 4th. 10 to the 6th millimeters to the 4th. Or my answer for Ix is just Ix is going to be equal to 7.2 minus 1.59 is 5.61, and the rest of the units just come along with it, times 10 to the 6th millimeters to the 4th, which would be our first answer for this. We're going to repeat that process for IY then. So IY would be IY for our rectangle, 1, minus IY for the semicircle, 2. So let's get those knocked out. IY should be, well, for our rectangle, we would have height times base cubed over 12. So our height here is 100. Height is going to be equal to, where am I at in my notes? 60 for the Y. Base times height cubed is the other way to put that. Base times height. Base always goes parallel to the axis of interest. So my base is 60, height is 100. So 60 times 100 cubed divided by 12. That's my I bar for the rectangle, plus my distance from the y-axis to the centroid would be half of the height here, half of 100, plus 50 d squared times the area times 100 times 60, minus my moment of inertia for the semicircle, or minus my y-axis goes parallel to the flat side of that semicircle, so I want to take my equation in my table here for Ix prime, because it's going parallel to the flat side. So it's kind of a messy one, but it is pi eighths minus 8 over 9 pi times our radius, 30 to the 4th, plus d squared a. So we just wrote down that I bar term in here. Plus, what's my distance from the y-axis to the centroid? Well, I can say from the y-axis to the flat side of the semicircle is 100. And the flat side of that semicircle is where my y-bar equation measures from. From x to the centroid, again, we've reoriented this. But we would say plus 100 minus 4r over 3 pi. 100 minus 4 times our radius is 30 over 3 pi. That's our d distance. I need to square that. Squared times the area. Pi times 30 squared. Pi r squared. You know, I get a long, messy thing. Go slow and steady with that. We can get through that. This would get us that my IY is going to be equal to, this first one gets us 20 times 10 to the 6th millimeters to the 4th. My second one is going to get us 10.86 times 10 to the 6th millimeters to the 4th. Or altogether, my IY is going to be equal to 9.14 times 10 to the 6th millimeters to the 4th, which should be our final answer for our problem. Hopefully this was a useful video for you. If it was, hit the like and subscribe. Let's watch some more videos. Get you an A with JJ.